Pick up a stainless steel spoon, run it under water, leave it wet on the counter, come back an hour later. Nothing has happened. No rust, no brown streaks, no deterioration of any kind. Now imagine the same experiment with a regular iron nail. By tomorrow, it would be orange with rust. By next week, flaking. The spoon and the nail are made of essentially the same base material, iron. The difference is not quality or cost. It is a single design decision made during manufacturing. One that happens to be one of the cleverest tricks in materials science. The real question is not why the spoon stays clean. It is what was added to the iron to make it behave so differently from its natural state. The answer is simpler than most people expect, and stranger too. Let's get into it right here on Small Things. Iron with one important addition. At its core, stainless steel is iron given a way to fight back against the thing that destroys it, oxygen. Left to itself, iron rusts. It reacts with oxygen and moisture, forming iron oxide that flakes and works through the metal until nothing solid remains. Stainless steel is iron with at least 10.5% chromium by weight. That sounds like a small change. The result is not small. Chromium reacts with oxygen far more eagerly than iron does. Present in the alloy, it claims the oxygen first, forming a thin, stable layer of chromium oxide that seals the iron from the atmosphere. That layer is invisible. It is thinner than a wavelength of light, and it is doing all the work. The discovery nobody expected. It did not start as a planned breakthrough. Steel had been in industrial production since the 19th century, building bridges, railways, and the frames of the first skyscrapers. But it had one persistent, expensive, and dangerous problem. It corroded. Bridge engineers spent enormous resources replacing rusted sections. Factory equipment in contact with acids or moisture degraded quickly. Medical instruments had to be boiled and treated constantly because ordinary steel was porous enough to harbor contamination after cleaning. Metallurgists across Europe and America were searching for a corrosion-resistant steel, approaching the problem from different directions at roughly the same time. In Sheffield, England, a metallurgist named Harry Brearley was working on a different problem, developing a steel alloy with better resistance to erosion from the heat of rifle barrels. In 1913, he began testing alloys with different chromium contents. Most failed to solve the erosion problem. But while reviewing and discarding rejected samples, he noticed something unexpected. Some of the chromium-rich specimens were not rusting. Weeks after being left in the laboratory, they remained clean and bright while other samples had turned orange. He recognized what he was looking at. He tested the alloy on a cutlery knife. It stayed clean in contact with food and vinegar that would have immediately stained ordinary steel. He brought it to a local cutlery manufacturer. The name stainless steel was coined not by Brearley himself, but by a company manager who saw the knife and simply called it stainless. Similar discoveries were happening in Germany and France in the same period. The chromium-iron combination had been known to chemists since the 19th century, but no one had turned it into a practical manufacturing process until multiple teams converged on the answer almost simultaneously in the years just before the First World War. Within a decade, stainless steel was in production for cutlery, surgical instruments, and industrial chemical equipment. Within a generation, it was in every kitchen, every hospital, and every major structure in regular contact with water and air. Architects specified it for building facades. Food manufacturers lined processing equipment with it. Surgeons replaced their carbon steel instruments with it. The metal Brearley almost threw away in 1913 is now the most produced corrosion-resistant alloy on Earth. Global production today exceeds 50 million tons per year, and virtually every major industry depends on it at some point in its supply chain. The invisible layer doing everything. So how does a thin layer of chromium oxide actually stop rust? Think of it less like a coating and more like a living seal that repairs itself. When stainless steel is exposed to oxygen, the chromium in the alloy reacts faster than the iron does. The chromium oxide that forms is extremely thin, transparent, and so tightly bonded to the surface that it is physically difficult for water or oxygen molecules to pass through and reach the iron below. The layer is not something that is applied during manufacturing and then might flake away with use. It forms spontaneously and continuously whenever the surface is exposed to air. If the surface is scratched, cut, or abraded, the chromium oxide layer reforms almost immediately on the newly exposed surface. The seal repairs itself. This is fundamentally different from how painted or galvanized steel protects ordinary iron. A painted surface protects the iron only as long as the paint is intact. Scratch through the paint and rust begins at that point and spreads outward beneath the coating. Scratch stainless steel and the chromium oxide reforms before the corrosion has time to start. The manufacturing process is designed to ensure that chromium is evenly distributed throughout the steel, not just at the surface. This is achieved during the melting stage, where ferrochrome, an alloy of iron and chromium, is added to molten iron in precise proportions. The mixture is then purified through a process called argon-oxygen decarburization, which removes excess carbon and other impurities while controlling the temperature carefully enough to prevent the chromium from oxidizing before it is needed. The result is a steel in which chromium is distributed throughout the entire material, so that wherever the surface is breached, the protection regenerates. Other elements are added for specific purposes. Nickel improves the overall corrosion resistance and gives the steel a brighter surface. Molybdenum enhances resistance to the kind of localized corrosion called pitting, which is especially important in marine or chemical environments. Each addition changes the balance of properties, which is why different grades of stainless steel exist for different applications. Stainless does not mean rust-proof. The assumption most people carry about stainless steel is that it simply cannot rust. That the name stainless is a statement of absolute immunity, not relative resistance. That assumption is not quite right. The chromium oxide layer that protects stainless steel depends on having access to oxygen to maintain and reform itself. In environments where oxygen is excluded, such as narrow crevices or the space beneath a washer or bracket that is never exposed to air, the layer cannot regenerate. Corrosion can begin in those gaps. Engineers call this crevice corrosion, and designing around it is a real concern in stainless steel construction. In extremely high chloride environments, such as the spray zone of a coastal structure or equipment, in contact with strong salt solutions, chloride ions can penetrate and locally break down the chromium oxide layer faster than it can reform. This is why marine-grade stainless steel, which contains added molybdenum to resist chloride attack, is specified for coastal and offshore applications instead of standard grades. Stainless steel can also be damaged by contact with ordinary carbon steel. If steel particles from tools, storage surfaces, or machining operations become embedded in the surface of stainless steel, those particles will rust, and the rust can initiate corrosion in the surrounding material. This is why stainless steel fabrication workshops keep stainless and ordinary steel completely separated. The material is not magical, it is well-engineered. And like all well-engineered things, it performs reliably within the conditions it was designed for, and less reliably when pushed beyond them. Everywhere you touch the modern world. Today, you will find stainless steel in almost every environment where metal meets moisture on a daily basis. The kitchen is the most familiar setting. Sinks, pots, knives, cutlery, appliance surfaces, all relying on the same chromium oxide layer Brearley observed in 1913. Every time a sink fills with water and drains, the stainless steel remains clean without any coating, paint, or treatment beyond its own chemistry. No maintenance, no special care. The layer reforms automatically. In medicine, stainless steel is standard for surgical instruments, hospital surfaces, and medical device housings. It can be sterilized repeatedly by heat, steam, and harsh chemical agents without degrading. Hundreds of millions of surgical procedures have been performed with instruments made possible by the discovery Brearley almost discarded. In construction and architecture, the Chrysler Building's iconic upper crown, clad in stainless steel in 1930, has never been painted or refinished. It has protected itself for nearly a century using chromium, oxygen, and an invisible layer thinner than light. In food processing, brewing, and pharmaceutical manufacturing, stainless steel lines every surface contacting food, drink, or medicine. Because it does not corrode, does not contaminate, and meets the strict cleanliness standards those industries require. A single contaminated surface in a pharmaceutical plant can compromise an entire production batch worth millions of dollars. Stainless steel makes that risk manageable, reliably, without coatings that wear off or paints that chip. One iron taught to protect itself. So how is stainless steel made, and what gives it the ability to resist rust? By adding one element that changes how the metal relates to oxygen entirely. Iron rusts because oxygen claims it. Stainless steel stays clean because chromium claims the oxygen first, forms an invisible seal, and reforms that seal whenever it is disturbed. The manufacturing process, from iron ore through molten steel, chromium addition, casting, rolling, and finishing, exists to ensure chromium is distributed evenly throughout, so that wherever the surface is exposed, the protection is already there. Stainless steel is not magical because it avoids oxygen. It is remarkable because it uses oxygen to protect itself. What looks like a simple shiny metal is ordinary iron, redesigned with an invisible shield. If this changed the way you think about something you use every single day without a second thought, let us know in the comments what everyday material you want us to look at next. We might make it our next episode. Thanks for watching. History often hides in the smallest details.